Ladies and gentlemen, it's a pleasure for me to give you some detailed information on shockwave physics, including cavitation. So let's start the presentation. I have to work this. The content is the acoustic waves or pressure waves, focused shock waves, radial pressure or shock waves, and cavitation. Now let's go on. It starts with sound, because you can hear the shock waves. So it's acoustic wave, and the more general, it's a pressure wave. And if you look now on the spectrum, the frequency range of sound, so you can see that the green area here, this is from 20 to 20,000 hertz, is the audible sound. Infrasound is something you can feel but not hear. And ultrasound is everything above 20 kilohertz. Shockwave, as you will see later on, covers as a broad spectrum starting from low frequency to high frequency. Now, you have to have a look at this diagram showing how the sound waves propagate. The sound waves are density waves. So they propagate in this direction as an arrow here, but they oscillate in the same direction like here. So the density wave is propagating towards this direction. That happens basically in all materials, including water, tissue, and air. But for the later on, you will see in combination with radial or shock or pressure waves, these have also a component where the particles are oscillating perpendicular to the propagation direction. And these are transversal or shear wave. And they propagate only in elastic or solid materials, and thus also in the tissue. Now, regarding the propagation, the sound wave behave, or pressure waves, it's all the same, behave very similar to light. So they can break on bordering between two different materials, and this factor is even more stronger the more these two materials differ in their acoustic impedance. They can reflect like in a mirror, and they can be scattered by irregularities in the material. For us, it's important that the acoustic impedance is different, especially between the tissue and the bones, or tissue and stones, like in lithotripsy. And of course, tissue to the air, because tissue is basically very similar to water, and thus everything coming through the air is strongly attenuated and reflected. We see here the values for the air. The acoustic impedance is very low. For the tissue, it's significantly high, factor 1,000. And for bone, is even a factor 6 more. That means that always to get full energy transmitted into or propagating into the tissue, there mustn't be any air or air bubbles between your source of the shock wave and the target, the body. Now, here you can see the basics between regularly oscillating wave, which is an ultrasound. This is a regular pattern with only single one frequency. And compared to it, pulses, like here, the acoustic pulses, which are shock waves. Here you see that the signal is asymmetrical. In case of a shock wave, also this leading edge of the wave is very steep. And then there is a decay behind that. The repetition of these pulses is much slower compared to the frequency of ultrasound. And thus, there is no thermal effects. And also, there are no micro lesions or whatever, except maybe if you have very, very high intensities, similar like it is in lithotripsy. Now we go a step further. How can be shockwaves generated? You can observe them in the nature, for example, thunderstorm. They can be all generated by man. For example, this supersonic plane is passing through the sound barrier, so it generates a shockwave. And that is basically the key issue, how shockwaves are generated. If you have an object which emits sound and or pressure waves in general, and this particle is moving, so these, as you can see, the waves are getting denser, the wavelength shorter, and the faster the body is moving, they comes to the speed of the sound in the same media, then it becomes shockwave. And it can be seen here. Here the body is at rest. He is moving. This velocity is smaller than the velocity of sound. And finally, on the right side, the speed is higher than the velocity of sound. And thus, you can see here, shockwave is generated in the front. And if it's even faster, there are two shockwave fronts we are leaving from this moving body. And now we come to the practical generation of shockwaves. And the first principle how the shockwave being generated in Dornier lithotripsy at the early 80s of the last century was with a electro-hydraulic principle. That means here you see a spark gap, two electrodes, which is immersed in water, and by applying high voltage to these electrodes in the range of 20 kilovolt, the water between these two electrodes evaporate, so it's a damp bubble is formed, and this damp bubble expands very fast. And what you see here on the right is very high speed camera showing at 100,000 frames per second, so it's very fast process. And still, you cannot see the direct generation of shock waves within it. You can even have a higher speed to see it more in detail. So if you look at here at the frequency of 5 million frames per second, then between here, these two images, you see a sequence where the bubble, the damp bubble, is visible. And because this bubble is expanding faster than the sound in water, a shock wave is generated. And this type of generator is one where the shock waves is generated from the beginning on, from the center of these two electrodes. In other devices using a different principles shown later, it works a little bit differently. So here, the fast expanding bubble generates here the shock wave. For the other devices, it has to be formed by propagation. And it happens because when pressure waves is propagating through water, which has a special anomaly that the positive part of the waves is propagating faster than the negative one, a steepening effect takes place. And you can see it here, how the wave is sharpening and becomes shock wave after some distance propagating through water. And in addition to this effect, these waves are also focused, further increasing the amplitude of these shock waves. And you can hear here, this is the first shockwave source developed by Dornier, used for lithotripsy at the beginning. Then we have here the piezoelectric source, where there are piezoelectric elements, where you applied voltage across them. They change the thickness, generate a pressure wave, and this pressure wave propagates towards this center of the sphere, is focused and getting a shock wave shape. And finally, we have a third principle using electromagnetic, where you can have two different designs. One is using a flat coil, and then it's generating a planar wave, pressure wave, which is steepening up and focused by acoustic lengths to the focal area. And finally, the system developed by Stolz Medical, where this foil is a cylindrical coil with cylindrical foil around it, and the focusing happens by this paraboloid reflector. It has the advantage, especially at the beginning, that you had an opening in the center to better navigate and target the stones in former days. And further, it is had a better efficacy compared to the acoustic lens. Now here you can see principally how these shock waves are generated. Here the cylindrical coil, the reflector, coupling belly, where the water is inside, allowing propagation of shock waves without any distortions and loss, and the body. And you can see here, through the coupling cushion, the shock waves is focused into the target. And what we have is an effect in the focus in the depth of the body. That means there is a relatively low intensity of shock waves here at the surface, but high intensity at the target area. So only the tissue target, which has to be treated, is in the focus. Here you can see now how such a focused head looks like with a cylindrical coil. It's the handpiece of the door lift. Now here the pattern again. So it is just schematically a drawing, as you saw at the previous slides, with a high amplitude, positive amplitude in the range of 10 to 100 megapascal. That means 100 to 1000 bar, and very short length of the pulse in the range of 1 microsecond. And especially with the shock waves, this rising or leading edge of the shock wave is even much steeper, as you can see in the real image of the shock wave, and thus it's in the range of nanoseconds. And the fact that the signal is now very asymmetric, there is a very high race time. So results that it's not having a single frequency like ultrasound, 1 megahertz, 2 megahertz, but you have a very broad spectrum. There have frequencies from the very low to very high. So it's a broadband signal compared to the ultrasound, where you would have only one single line, only one frequency. And thus the wavelength is relatively short due to the short time in the range of 1.5 millimeter, resulting in the effect that the shock waves can be focused. Now we see here the typical interpretation how the focal area looks like. So it's typical that it's not only with this type of shockwave source, it is usually always ellipsoid in the direction of the propagation. And you can see two circles. The smaller one, is the focal area, which is specified like the area where the pressure is at least 50% of the maximal pressure. Compared, this is a relative measure, and there exists also absolute measure, so this 5 megapascal level, which has been many years ago, at the beginning of a shockwave uses medicine, set up as pressure where the people expected some biological effects. We now know that with our ESWT system, we might have effects even underneath this pressure. But it was former days a possibility to how to quantify this treatment area, also absolutely. It means this is a circle corresponding to this 5 megapascal pressure level. And as we will see now as the next, the focal area, the treatment area, And now it's important here, these first lines, this is a focal area relatively specified as 50% of maximum, which is in other words also known as -6 dB area. And this area is more or less always the same independently of your energy setting. So whether you have a low setting or high setting, this area is usually very similar. Compared to it with this absolute value with 5 megapascal, you can see here that with increasing intensity, of course, because it's an absolute measure, the area increases. So when you are increasing the intensity, your focal area remains the same, but the area where you might expect biological effects is becoming larger and larger. Now you see here typical sizes, dimensions of focal areas of different devices. There is a typical that the devices using the electro-hydraulic principles, it means with a spark gap, have a usually relatively long and broad focal area. On the other hand, the electromagnetic devices, the focal area is much narrower and typically also shorter, comparable to other devices. And finally, the piezoelectric devices have a very small focal area, as you can see here. It seems to be an advantage having a very precise shockwave focal area, but of course, it's make it much more difficult to hit the right target. On the other hand, with the electro-hydraulic systems where it's much easier to hit the target, you have the problem that the electrodes have limited lifetime, so have to be replaced more often. It's much significantly louder, and in most cases, it's also significantly more painful with the same intensity setting. Now we can see here how it looks like with, as an example, our sepia handpiece here. That is the pressure field in the direction of the propagation. You can see that the maximum pressure depends, of course, on the different energy settings. And now you can look here. One possibility to change basically the depth of the focal area is that you use some kind of a standoff. That's area, basically bodies, which cover the distance between the source and the tissue. And now I introduce now here this short standoff area, and now this distance decreased from 5 centimeters to about 35. And if I take a long one, it becomes even shorter, the distance. It's about only 15 millimeters. You can also change this distance by using a different handpiece. And it's interesting here also, if you look at this 5 megapascal level, you can see that in the case of this handpiece, at maximum setting, of course, you can reach a depth of more than 10 centimeters into the depth, of course, accordingly lower intensity compared to the maximum. Now you see here the other handpiece used with Dualis, the sepia C-actor. It has different reflector resulting in different shape of the pressure field, which is significantly shorter compared to the other one. So you hear, even at the very high intensities, this 5 megapascal depth is only in the range of 60 millimeters. And here is a 3D drawing of this pressure field or pressure mounting. This is also set. And you see here this 50% of maximum pressure is the focal area. Here's a propagation direction. And so you can basically compute the energy which is delivered in this area to some which is a diameter of approximately of the focal zone. or this is a red one, or if you would like to know the energy in the 5 megapascal area, it's of course much more larger circle, and the energy in this larger circle is accordingly higher compared to the energy with a small one. So it depends on which question you're asking. So far now we go to the second type of shock waves, which from physical point of view are pressure waves. They are usually generated ballistically by a projectile hitting a target, as a steady target, emboss. The speeding up of the projectile can take place by compressed air or also electromagnetically. Here you can see a system using pressurized air, compressed air. The projectile hits this target, this vibrates, and the vibrations, the pressure waves, are propagating into the tissue. But of course, in this case, we have only superficial effect, and the energy is decreasing from the point of entry into the body, which happens relatively fast. Again, here is a realistic sample of a handpiece using this compressed air generation of pressure waves. Here in front of is the emboss or transmitter, the projectile hitting it. And as you can see, this transmitter vibrates on behalf of the impact of the projectile. Now we have different types of transmitters, so radial transmitters. It's a full scope range here, and these transmitters differs in 3 parameters. They are using different materials: steel, ceramics, titanium. They're having a different shape, a large one, small one, and of course they have totally different designs. It means here it's the connection between the housing and the transmitter relatively stiff. He's very flexible. Here's this design also comparable to the Diecto system with a flexible connection. And this is a system where the transmitter is made of elastic material. Now we have a look theoretically on this transmitter. And the projectile hits this transmitter. First, there are vibrations generated within the material, and they partly can escape into the body. And these vibrations have typically high frequency because the speed within this material is usually significantly higher than in water or surrounding tissue. And it's in the range of ultrasonic signal in about 100 kilohertz, depending on material and the shape of the transmitter. This is a longitudinal wave. But this transmitter is, as I disclosed previously, also attached to the housing and can make macroscopic movement, macroscopic vibrations. And these vibrations have much lower frequency in the range of 1 to 10 kilohertz. And these vibrations are, of course, first longitudinal wave, but they contain also elastic or shear wave, which oscillates perpendicular to the propagation direction, as I show in the previous slides. So here again, we have 2 different vibrations generated in a radial pressure wave source. One, the fast one, the ultrasound component, in the range of, this is the spectrum again, in the range of 100 kilohertz, with typically much lower amplitude of 0.1 to 10 megapascal, 10 times longer pulse lengths, in spite of this small drawing. And the wavelength is approximately 10 times compared to the shock waves. It means that these pressure waves basically cannot be focused, because in order to be have a possibility to be focused, the source of these waves must be much larger than the wavelengths. And here we have dimensions which are comparable to the size of the source. The transmitters are in the range of 1 to 2 centimeters. Now we have the sonic pulse, the slowly one, which you can see here as basically the movement of the transmitter. So it's an excursion of it on behalf of the impact of the projectile. It's a very low frequency. The pulse is significantly lower, in the range of 0.2 to 5 milliseconds. And accordingly, the amplitude is even larger, 10 times larger compared to the length of the first ultrasound component of these vibrations. Now we can have a look how these physical properties influence these two types of vibrations. Here you can see the amplitude of the ultrasonic pressure alongside the z-axis. That means into the direction of the body. And here it's with about 1 bar driving pressure, you can achieve at the surface, at the point of entry, about 4 megapascal pressure. And this intensity, this amplitude decreases relatively fast. So that if we assume the same definition for the penetration depth as used for the definition of focal area, that means 50% of the maximum, then we come up here at 50% of the maximum pressure. It results with a penetration depth of less than 10 millimeters. Now compared to it, this is a steel transmitter, the R15, as we call it R15. Now you can see another transmitter, the D20S. This is a transmitter with an elastic, soft, basically attachment between housing and the transmitter. And you can see that the maximum pressure is slightly lower compared to the other one, but the decrease in the amplitude is slightly slower. That means that if you take again 50% of the maximum, the penetration depth is slightly higher, almost 20 millimeters. On the other hand, if you take this deep impact transmitter, it has very, very high intensity compared to the others. At the surface, in the range of 8 megapascal, but in the same principle of establishing the penetration depth, it is only a few millimeters. But you have to consider, if you would assume an absolute value of the amplitude, like the 5 megapascal with focused shock waves, and take 1 megapascal in this range, you would see that here you get relatively deep penetration depth. It's 1 megapascal, and here it's more or less comparable to the R15. Now another typical property due to the design of the transmitters is the shape of the field. And this field shape can be visualized by Schlieren images. It doesn't show the maximum intensity of these pressure waves, but it shows the rise edge of the wave. And so it discloses the shape. And you can see with these two transmitters, the shape of the pressure field is very similar and very radial. It's a spherical shape. In the next slide, we have a different transmitters, the 15 transmitter and the deep impact transmitter. And you can see that the shape of this pressure field is now narrower. So it's different compared to the other one. And it means that the energy is basically concentrated in a smaller diameter of the field. Now we have a look at these two diagrams. These are computed fields, pressure fields, at different vibration frequencies. And you can see here that of course, the intensity here is red, is go much farther compared to the other image on the left side, where the frequency is significantly lower. And so one would ask how it is with this slow sonic component of the radial pressure waves. This sonic component should have much shorter penetration depths compared to the other ones. But what we observe is that it's not the case. Even the longitudinal wave, when measured by force sensors, you can show that the penetration depth is similar between these two types of oscillations. And furthermore, due to the effect that the radial pressure wave and the small sonic component of it has also transversal wave, we will see here that this transversal wave has a significantly deeper penetration depth compared to the transversal longitudinal waves. So here is we have a transparent tissue phantom. On top you see the radial head, the transmitter. And schematically, you can see this source, illumination, and camera, which is visualizing basically how the shear wave or transversal wave is propagating into this phantom on behalf of a change of the surface here of the phantom. And comparing now the images of these wavefront, we can see that these wavefronts are, from intensity point of view, totally different depending of type of the transmitter. The strongest is with a D20 in this case. And we can also make some kind of visualization how this wave is propagating into the tissue, into this tissue phantom. And we will see that when we try now use the darkness of these images to take it as amplitude of these waves, we will see that the propagation, also the decrease of the intensity, is significantly slower compared to the longitudinal wave. In addition, this elastic or transversal wave is propagating much slower compared to the sound wave. And this speed is depending of elasticity. So this here, this 7 to 10 meters is typical for materials with elasticity comparable to muscle tissue and soft tissue. The stiffer the materials, the faster will be this speed. We can also visualize it now in video. So it is now the wave generated by the R15. On the right hand side, you see how the wave is propagating from the Electro-20. It's much stronger wave. The variations after that are, of course, due to the reflections on the boundaries of this phantom. Now we have a short look at the energy which is available or which are basically propagating into the tissue. Here we use so-called ballistometer. It uses the principle of Newton's cradle. So it means that this moving body gives this energy to these balls in the center. And finally, on the right side is transmitted to the last ball, which is free. It can move again from here. In this case, we have the first ball corresponds to the projectile. Then we have the transmitter, that is in the case one ball in the center. And then we have the weight mass, which is this can fly up. And the height of this mass, the height how this ball basically can rise, is a measure for the energy which comes from the bottom from the projectile. Now we can here see calculations. This is a calculation on behalf of the projectile speed. And you see that there's a lot of energy which this projectile is carrying with it. But it's take a lot of this energy back because it's just spring back from the transmitter due to the large difference in mass between the projectile and the transmitter. And now we here see calculated energy which is within the transmitter, and the yellow one is which can be measured by means of this ballistometer. And this is the energy which basically can enter the body. Now we can calculate this independently on behalf of the pressure fields. And now we can see here that the energy at 5 bar of the radial transmitter in the range of 6.5 millijoule. Compared to it, the sonic energy, basically energy of the slow part of the radial pressure waves is more than 10 times higher. Interestingly, compared to the focal shock waves. So if we take a small area which is comparable to the diameter of the focal area in 0.555 millijoule, there are 18 millijoule, and here we can see that as usually communicated, the energy of the radial pressure waves is significantly lower than this one. But when we consider the total energy of the radial pressure waves, then it is even higher than the energy delivered by the focused shock waves. And here is another number generated on behalf of this fixed parameter of 5 megapascal at higher frequency. And finally, repetition more or less what I've said, and visualizing the key difference is that with focal shock wave we have a maximum of energy at the position of the focal point. And with radial pressure waves or shock waves, we have the maximum at the point of entry. And that is the only question, how fast is basically this intensity decreasing. And now to the special chapter, cavitation. Cavitation basically describes formation of bubbles. And we can see here that there are two types of cavitation. The the bubbles forms due to negative pressure, and this means that it's not only shock waves can generate cavitation. It can happen also at different physical conditions. And secondly, the cavity can of this cavity due to the negative pressure can fill with vapor, or it can be filled by gas who basically escapes out of the media, out of the fluid typically. And so we distinguish between so-called soft or stable cavitation. These are bubbles which are filled with gas. And because the gas cannot be diluted very fast again into the surrounding fluid, then it takes time and it's called stable cavitation. On the other hand, there is hard or transient cavitation, where these bubbles are formed by the vapor of the surrounding fluid. And these bubbles can collapse very fast, even generating shock waves of themselves, and they have a much more destructive capacity. Here you can see an example of observation with a lithotripsy, where the shock wave is passing through the fluid, or urine more or less. And here these bubbles, cavitation bubbles, can collapse and generate by themselves very local shock wave. It's the expectation that this effect, combined with the forming of jet streams, are contributing to the disintegration of the stones. You can see the more schematically the bubble is compressed, and when it's collapsed here, it expands as a shock wave afterwards. When the bubble is close to the solid surface, it means a stone, then it's not collapsing symmetrically but asymmetrically, and it forms some kind of a jet, and this jet stream is very fast, very destructive, and is one of the cause of the stone disintegration, as far as we know, even if there are different theories how the disintegration really takes place. Here's a really photograph of such an effect, and you can see here this jet stream formation in the center of the bubble. The speed of these jet streams is up to 100 to 700 meters per second. That is very fast. And now when cavitation takes place, I mean this destructive transient cavitation, where the water damp is formed, from the theoretical point of view, one would need a negative pressure of 1000 megapascal. This, of course, in the nature not achievable. In experimental, in the lab or the nature, you can achieve this effect with a lower pressure, and it depends always on the conditions. Usually there are some impurities in the water, or there is still some slightly microbubbles due to the diluted gas, and thus this pressure can even be lower in the practical application. But what we are interested in, when these effects can take place in the tissue. And here we see diagrams where the cavitation or the bubbles formation being investigated in water. And you can see that in relatively water without diluted gas in the range of 20 megapascal, and with saturated water with nitrogen, with oxygen, this value is significantly lower. That means that here, of course, is no more hard or transient cavitation taking place, but stable cavitation. I mean, stable cavitation happens, for example, when you shake a mineral water bottle and open it, and the water comes out with a lot of bubbles. That is stable or soft cavitation. And now we want to see how it looks like when we go to the tissue. And you can see that to achieve some kind of cavitational effects in the tissue, you need even significantly higher negative pressure. And thus we can summarize also on behalf of practical experience that in the tissue, typically only stable cavitation can be generated in fluid with a lot of gas diluted in like blood. And you see the experiment with kidney, where we have a lot of experience due to the treatment with stones, kidney stones, with shock waves. And as in many circumstances, we observe also formation of hematoma. Interestingly, when we now, due to the pre-shock or some kind of pre-warning to the tissue, the ramping of the shock waves, vasoconstriction results. And that means that the blood is basically pressed out of the tissue, and all of a sudden the hematoma or the stable cavitation is almost not observable. Thus, here again we see these three different types of shock waves. There's a very high intensity shock wave for lithotripsy in the range of 150 megapascal positive pressure, and accordingly almost 20 megapascal negative pressure. This is the dualists. We have this scale is of course smaller. We have lower positive intensity, but also the negative pressure is lower. And with the orthotronic component of the radial pressure waves is even significantly lower. So now we can put a line at 20 megahertz. When the cavitation starts to take place, we can see that the lithotripsy is just in the range when this can happen, depending, of course, as I said, on impurities and diluted gas. With dualet is basically not possible, and with radial pressure waves is not possible at all here. So this stable cavitation can, of course, cause a damage. One example with no relation to shock waves is, for example, the decompression sickness or diver sickness. When the diver is coming too fast out of the great depth, he has a lot of nitrogen diluted in his blood, which basically gassed out. It forms stable cavitation and causes accordingly, due to the bubbles, vessel rupture and destruction of the tissue. This is the hemorrhage as shown with kidneys, and of course it can also result in cell rupture in the case of the fat cells. Thus, finalizing and a summary take-home message is a soft tissue stimulation, the mechanotransduction, which is considered the effect how the shock waves or pressure waves are stimulating the healing process by releasing growth factors and increasing cell metabolism, stimulating stem cells and immune system, is not as a result of cavitation. Cavitation always results in some destruction of the stone, of the tissue, of the microvessels, or tissue at all. Thank you for the attention.
Pavel, that was incredible. Can you switch your screen back?
Yes. Okay.
And if you stop sharing.
Good.
If you stop sharing.
Pardon me?
If you stop sharing your screen.
Okay. Stop sharing.
Yeah.
Good.
Perfect. Okay. Now we are back. So, Pavel, that was brilliant. Do you mind if I ask just a couple of questions?
Okay.
Yeah. Just to
make it fast. Yeah. Okay.
Yeah. Just to clear up this point. So, what you've said quite clearly is it is impossible to create cavitation with either radial pressure waves or focused shock waves.
It's never say never again. I mean, it's according to special conditions, you can cause cavitation, but the only cavitation you can observe in the tissue is probably due to the hemorrhage and due to the destroyed vessels. That is the only negative effect you can observe in practical situation, and this is obviously due to the soft cavitation. And even this hard cavitation, which is usually reported on in lithotripsy, is measured in the laboratory, but not in the body, in the urine or whatsoever, because this area is not directly accessible.
So, what do you think about shockwave machine manufacturers saying that cavitation is being produced and that's the reason for tissue healing?
The cavitation is definitely not the origin of tissue healing. So you can basically generate in laboratory and special conditions soft cavitation with radial, because this you can just put your transmitter into the mineral water and it will bubble up. And you can, of course, also generate as the very surface of the transmitter, and depending on transmitter and intensity, also on the transmitter. But this you can see only with very high-speed camera, because these bubbles need just microseconds to disappear again.
So, as we've been teaching for some time, the therapeutic effect of shockwave is mechanotransduction,
Correct.
leading to the release of growth factors and microscopic circulation increases and all the things we discussed before. And from what you're saying, the shockwave that comes from a focus machine is much more powerful than the pressure wave that comes from the radial machine, and the focus shock wave can go much deeper into a focal area, whereas the radial pressure wave is lost very soon after it passes the skin.
Except for this elastic or shear wave, where we now don't have a direct scientific feedback how they really act or react with the tissue. But you can observe it on your own experience if you apply, for example, the ecto, which is a large amplitude of excursion, and you can see that basically there is, you can feel this vibration on the other hand of the arm.
Yeah.
So you have a deep effect, of course. How far is this deep effect of this shear wave really have a therapeutic effect is open at the moment.
Ah, that's very interesting. So some of the studies coming out at the moment, particularly for radial pressure wave, are showing equal results to focus shock wave. And your point is that this might be down to this shear wave rather than the immediate pressure wave.
It might be, but this is a hypothesis, of course, which has to be proved or withdrawn so far. I mean, it's definitely that these waves, which are comparable to some extent to the shock waves, have a very relatively low penetration depth. So, of course, in pain, where you have also very superficial targets, it can be assumed that it's maybe same working principle. If you have a deeper targets, it should depend on different effects.
Very, very good. And one last point, and then I'll let you get back to your life. The different transmitters. So the deep impact transmitter, and I show in a video how high that can flip a coin, yes, compared to the standard transmitter where it flips a coin very, very low. What are we seeing there when we see this penny coin flick really, really high? Is that just the transference of pressure through the material?
This is a transmission of energy from one body, from the transmitter to the coin. And it's basically demonstrate what I tried to show in these calculations. Then the energy released by the radial pressure wave, total energy released by the pressure waves is higher compared to the shock wave. But of course, it's two components, the ultrasonic component and the sonic component. And so it's a higher jump is showing just there is more energy coming, but different type of energy at the same time.
Okay. And is there a comparison between bar pressure and energy flux density, or millijoules per millimeter squared? Because the radial pressure wave and the focus shock wave are measured differently on the machine. One is measured in bar pressure, the other one is millijoules per square millimeter. Could we say that 0.1 measured as millijoules per square millimeter on the focus machine is the same as a certain bar pressure?
Of course, you can also express the energy of the ultrasonic pulse is in millijoule per square millimeter, and you can do it even if it's not a common sense also for the sonic component. But I believe that these numbers are not the best measure for the effect to the tissue. And I assume that it's more the total energy delivered to the body which matters, and maybe some minimal level you need to basically like the 5 megapascal, the minimal level you need to have some effect on the tissue. And therefore, at least also to distinguish for the focus shockwave, we try to introduce one measure for which for the energy is the impact, which is expressed in millinewton seconds, and it's basically it's the impulse, but the impulse is very closely related to the energy. And interestingly, there is now, I guess last year, a paper published by Dr. Wess, where he investigated the effect of shock waves for disintegration for stones. And he could also show that in the case of the shock waves, also this impact, the energy of the impact, might be the key parameter for the efficacy of the stone disintegration. So it might be some common value. So in general, energy and maybe expressed as impact or as momentum.
I understand that. So we don't have, or we do have, a straight correlation. Is 5 bar pressure on a radial machine equivalent to, say, 0.25 millijoules per millimeter squared? So would that be similar or not?
As I said, you would have to distinguish whether you add up the energy of the sonic component and the ultrasonic component. For the ultrasonic component, it's typically there are calculated values which you could compare. But of course, the sonic component is just a part of energy delivered by the radial pressure waves. Then it's a question whether this value is really representative value for the treatment outcome.
Gotcha.
I don't know.
Yeah. Pavel, it's been an absolute pleasure. I feel like this is something of a steal for us to have got you this evening. We've taken up a lot of your time, and I cannot thank you enough for allowing us to do this presentation and for me to ask a few questions afterwards. So thank you very, very much on behalf of everyone that watches this.